Argand diagrams are a type of diagram that is used to represent complex numbers. So in Argand diagrams, we have the imaginary axis over here and the real axis over here. It's basically like the Cartesian system. We have a horizontal axis. On that we represent the real part of the complex number, and in the imaginary axis we get the imaginary part. So for any complex number z, it's represented as x plus iy. So for any xy, the x value is the real axis value and the y value is the imaginary axis value. So this line over here represents, this line or this point over here represents x plus iy. Now if I move on to some advanced cases of it, we have this formula over here. This is the formula of a circle in an Argand diagram. This represents a circle. In a case like this, we represent z as x plus iy. X and y are variables over here, and z1 is a plus ib. In this case, a and b are constants, not variables. So basically z1 is a fixed point. So z is any point on this diagram, whereas z1 is a fixed point. So suppose this is z1, it's fixed over here. So it's a and b. For a form like this, the center of the circle will be at a comma b and the radius will be r. So if I want an example of this, suppose I have z minus 1 plus 3i equals to 3. From what we have here, we can see that this is in the form z minus 1 minus 3i equals to 3. So this is z1 over here. So our center will be at 1 comma minus 3 and the radius will be equal to 3, and we can prove it here as well. We know that z is x plus iy, so I can just replace it with that, and then we have minus 1 plus 3i. I'll gather the real parts together, so that's x minus 1, and the imaginary parts together, so that's I y plus 3. Now if you know how to find the magnitude of a complex number, it's just using Pythagoras theorem with these two values. So the magnitude of this line, I can show it on the diagram as well. So if I want to find the magnitude of this line, suppose it's 3 plus 1i, so 3 plus I. If I want to find the magnitude of this line, basically the distance of this, I'll need to use Pythagoras theorem. I know that this is a right angle, this length is 3, this length is 1. So the length of this line will be root over 3 square plus 1 square. We'll use Pythagoras theorem over here. Similarly, we'll do the same here. So I get x minus 1 whole square plus y plus 3 whole square. You can let go of this I here. The I does not matter in the magnitude, and this will be equal to 3. Now I can square both sides. If I do so, I'll get x minus 1 squared plus y plus 3 squared equals to 3 square. And if you remember the equation of a circle, this is it. This is the equation of a circle with a center at 1 comma minus 3 and the radius of root over 3 square, which is just 3. Now another type of equation for an Argand diagram is that of perpendicular bisectors, and it is given in this form. So I have z minus z1 equals to z minus z2. So the magnitude of z minus z1 is equal to the magnitude of z minus z2. And if you think about it intuitively, this will intuitively come out as a perpendicular bisector. So let's see why. So we draw a diagram over here. This is the imaginary axis, the real axis. Suppose z1 is over here. This is z1 and z2 is over here. Now for any z, I want this length z minus z1, the magnitude of this, and the magnitude of this blue, which is the magnitude of z minus z2. I want both of these distances to be the same. So at any point, it will be equidistant from z1 and z2. So for all points, the red and blue lines will have the same length. And this only happens if the line is a perpendicular bisector to z1 and z2. So something like this. This is a better line. So this will be 90 degree. So all four of these angles will be 90 degree, and this is a perpendicular bisector to z1 and z2. So this line that's found by this equation is just the perpendicular bisector to this line segment, the one that joins z1 and z2. Now we have another common one. This is a half line, so it's given by this equation. So we have the argument of z1 minus z1 being equals to theta. Argument is basically the angle from the horizontal. So if I have an Argand diagram over here and a line here, its argument is this angle from the positive real axis, and you move anti-clockwise. If you move clockwise, it's negative. So for a line like this angle will be negative phi or something. So for this line, it will be a half line that begins at z1. So if I show an example, suppose I get argument of z plus 3 plus 2i is equal to 3 pi by 4. If I convert it into the form we had, we get arg z minus 3 minus 2i equals to 3 pi by 4. So I'll draw another Argand diagram. This point over here is minus 3 comma minus 2. So I'll plot it in my diagram. Minus 3 on the real axis, minus 2 in the imaginary axis, so it's over here. And the angle we are given is 3 pi by 4. If I convert it into degrees for understanding it better, I get 3 pi by 4 multiplied by 180 by pi. From here we get 135 degrees. So it's an obtuse angle somewhere here. This is where we take the angle from. We take the angle from the horizontal. So this angle over here is 135 degrees or 3 pi by 4 radians. and this is the line that we want. So the line that keeps on going from this point, which is -3 comma -2, and at an angle of 3 pi by 4. So in general, for a case like this, the Argand diagram will be starting from A comma B, and it will move at an angle of theta to the horizontal. So this is the diagram we have if Z1 is A plus BI. Now the fourth case is another circle over here. We have another way to represent circles using complex numbers, and it's this form. It's very similar to the perpendicular bisector with a slight difference. So this is the same for perpendicular bisector, but the difference you have is you have a constant in the front, and the rule is that the constant cannot be 1, because if it's 1 it just becomes a perpendicular bisector. So the value of k cannot be 1. Now I'll show an example to you to show why this is the case. So suppose I have z plus 4 minus 2i over here equals to 2z minus 2 minus 5i. I'll use x plus iy in place of z. Z is x plus iy. Do the same on the other side. Now I'll group the real and imaginary parts together. So we get x plus 4 plus I times y minus 2 on this side. On this side we get x minus 2 plus I times y minus 5. Now I'll use Pythagoras theorem to calculate the values. So I get x plus 4 whole square plus y minus 2 whole square equals to 2 times root over x minus 2 whole square plus y minus 5 whole square. Now I can square both sides. So I squared this and I squared this. If I do that, on the left I get x plus 4 whole square plus y minus 2 whole square, and on the left I get 2 square multiplied by x minus 2 square plus y minus 5 whole square. Now I'll expand the squares. The first one gives me x square plus 2 times x times 4, so 8x plus 4 square is 16. Now expanding the next one, I get y square minus 4y plus 4. On this side I get 4 multiplied by x square minus 4x plus 4 plus y square minus 10y plus 25. So on the left I have x square plus 8x plus y square minus 4y. I'll add the constants together. I get plus 20. On the right I get 4x square minus 16x plus 16 plus 4y square minus 40y plus 100. Now I'll move everything on the left to the right. So 0 is equal to 4x square minus x square minus 16x minus 8x plus 4y square minus y square minus 40y plus 4y, and finally I have plus 100 plus 16 minus 20. So I get 3x square minus 24x plus 3y square minus 36y, and finally plus 96 equal to 0. We can factor out 3 from here. I get x square minus 8x plus y square minus 12y plus 32 equals to 0. Now to convert this into an equation of a circle, I can complete the squares over here. So for x I get x minus 4 whole square minus 4 square, and for y I get y minus 6 whole square minus 6 square plus 32 equals to 0. So we get x minus 4 square plus y minus 6 whole square. This will be equal to 16 plus 36 minus 32. So 4 square plus 6 square minus 32. We get x minus 4 whole square plus y minus 6 whole square equal to 20. So this is a circle with a center of 4, 6 and radius of root over 20. So we just showed how this will be a circle, and this will be the case for any k other than 1. Now the final type of equation that we'll visit before we move on to transformation is this. So if we have the argument of z minus z1 divided by z minus z2 equals to theta, this will be an arc of a circle. And the endpoints are z1 and z2. Now let's see why that's the case. Argument of z minus z1 divided by z minus z2 can also be written in this form. So z minus z1 minus argument of z minus z2. This will be theta. Now if the argument of z minus z1 produces an angle of theta 1 and argument of z minus z2 produces an angle of theta 2, if you go back you can see that these are equations for half lines. So both of them are half lines that start at z1 and z2 and have an angle of theta 1 and theta 2 respectively. So if this is theta 1 or z1, this is theta 1, and I have z2 with theta 2. This angle over here will become theta 1 minus theta 2, and we can show that as well. Since this is a straight line, this angle will be 180 minus theta 1, and we know that theta 2 plus 180 minus theta 1 plus this angle x will add up to 180, since these are interior angles of a triangle. So I have theta 2 plus 180 minus theta 1 plus x equals to 180. If I keep x on the left and move everything else to the right, I get 180 minus 180 plus theta 1 minus theta 2. So x ends up becoming theta 1 minus theta 2. This angle is theta 1 minus theta 2. It's evident in the formula as well. We have argument of z1, z minus z1 as theta 1. Then we subtract the argument of z minus z2, which is theta 2. And this is equal to theta. So this is theta, which is theta 1 minus theta 2. Now this isn't the only angle that it will work for. If this is my theta 1 and this is my, well, they'll be from the same points. So let me redraw this at another angle. So I have another angle theta 1 and another angle theta 2. My theta is still the same, but it's at a different point. So if you follow it, it will end up becoming an arc of a circle that begins at theta z1 and ends at z2. So this is an arc of a circle. So at any point on this arc, these two lines meet. This is the case. And you need to notice that the endpoints of the arc are z1 and z2. Now, an important question might be to find the equation of the circle that this arc is of. So I'll do an example. It will be a long one. So if I have argument of z minus 6 divided by z minus 2 equal to pi by 4. I'm not taking any imaginary component for this to keep it simple because the working will be long anyways. So before we do this, I can change the representation of this. So before we find out the argument, let me change z minus 6 divided by z minus 2 into x and y. So I get x plus iy minus 6 and the denominator is x plus iy minus 2. From here I get x minus 6 plus iy divided by x minus 2 plus iy. Now we can rationalize this by multiplying x minus 2 minus iy. So we'll do it at the top as well. Now in the denominator we'll get x minus 2 whole square minus iy whole square, because this is just a plus b multiplied by a minus b, where a is x minus 2 and b is iy. This is equal to a square minus b square. On the top we'll have x minus 6 multiplied by x minus 2 plus x minus 6 times minus iy. So this is y. So we'll change the sign in the front. Then we have plus iy multiplied by x minus 2, and finally I have plus iy multiplied by minus iy. Now for the denominator I get x minus 2 whole square. Now minus iy squared is basically minus I square y square, and you know that I square is just minus 1. So this is minus minus 1 y square. So this just turns out to be plus y squared. And on the top we have x square minus 6x minus 2x plus 12. And for the imaginary part we have plus I. Here we have minus yx minus, so plus 6y. Then we have plus yx here and then minus 2y. So I'll separate it out, the real and imaginary parts. We have x minus 2 square plus y square. The numerator will be x square minus 8x plus 12 plus y square. And for the imaginary part we'll have x minus 2 whole square plus y square in the denominator as well. And on top this yx will cancel out, so we'll just have 4y. Now we have rearranged the inside part of this. So we have rearranged z minus 6 divided by z minus 2. We can now replace this over here. If we do that, we'll get that the argument of this expression we have found in the last line so we'll write that down now. This will be equal to pi by 4. Now if we think of an imaginary number, so the argument of a plus bi equals to theta. We know that tan theta will be equal to b divided by a. So we can use this property now. And if you want to see where this property comes from, we have our Argand diagram. So we have this point over here, which is a in the real axis, b in the imaginary axis. Now this angle theta will be equal to opposite divided by adjacent. The opposite is equal to b and the adjacent is equal to a. So this is tan theta equals to b divided by a. In our case, a is this part over here, the real part, b is this part over here, the imaginary part. So we'll get tan pi by 4 equals to b divided by a. So we have 4y divided by x minus 2 whole square plus y square divided by x square minus 8x plus 12 plus y square divided by the same numerator. Now you can flip this in the bottom and write it as a multiplication as well if you want, or you can notice that you can cancel out the denominators because they are the same. I'll show the extended step because I have something in this form. So this can be written as a times b. So I can turn this division into a multiplication if I flip this around or find the reciprocal of the denominator. So nothing complex, I'll just flip over the denominator and write it down like this. Now x minus 2 whole square plus y square will be on top, whereas this part over here will be on the bottom. Now you can see why we can cancel out the denominators. And finally we get 4y divided by x square minus 8x plus 12 plus y square. And we know that this is equal to tan pi by 4, and that's equal to 1. We know the value of this, it's 1. And we are doing it in radians, keep in mind. So I can cross multiply now. So I'll get x square minus 8x plus 12 plus y square equals to 4y. Move the 4y over to the left. So I get x square minus 8x plus 12 plus y square minus 4y equals to 0. Now we can complete the squares like we did previously. So in this case we'll get x minus 4 whole square minus 4 square plus this 12 we had previously plus y minus 2 whole square minus 2 square equals to 0. We get x minus 4 whole square plus y minus 2 whole square, and then we get a minus 8 over here. So we get a circle with this equation. So we just get the circle with center 4, 2, radius root over 8. This is the circle that this arc is of. So this arc over here is from the circle with this equation. It's the circle with center 4, 2 and radius root 8. Now there's a property based on the angle we have over here. So if I have arg z minus a divided by z minus b equals to theta, if theta is equal to pi by 2 or 90 degrees, it will basically be a semicircle like this. So the arc we subtend will be a semicircle, and this is because of the property you might have learned before as well, that the angle subtended by the diameter is 90 degree. So the angle subtended by the diameter at any point in the circle will be a 90 degree like this. And if theta is less than that, so theta less than pi by 2 or 90 degrees, it will be the major arc. So it will be like this. It will cover the majority of the circle. And otherwise, if it's greater than pi by 2, we'll have the minor arc, so the smaller part. And the reason is that if we look here, any angle subtended will be an acute angle if you visualize this. On the other hand, anything subtended here will be an obtuse angle. It will be more than 90 degrees. You can visualize it as well here. So these angles over here are acute. This is the reason that if theta is less than pi by 2, it's the major arc. If it's more than pi by 2, it's the minor arc. And if it's exactly pi by 2, it's half the circle. These are the common graphs that you'll go through in any topic of further Argand diagrams. I'll cover transformations of the complex plane in a later video because it's a whole new topic with various different things. But before we go there, you need to be familiarized with all the different shapes of graphs over here. So have a look through this video before you move on to the next part.